Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math basic course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Stepping aside as we jump into section 11.3 in the Big Ideas Math Integrated Math 2 textbook, Areas of Polygons. And I'll tell you what, this section for me is a long time coming. I've taught integrated math stuff now for the past, I think, 4 or 5 years, and never have I been able to actually touch on the subject. I haven't taught this section of something in probably 9 years or so. It's been a while for me teaching a regular conventional geometry class and letting this one happen. I'm excited to do it a little bit because when I would teach IM3 and we would do solids of volumes and stuff, and by the way, that comes up I think next in 11.4, we do volumes of solids and stuff like that. I was always like, oh, if I have an area of a regular hexagon, I can't tell you how to do this because you haven't learned it yet, so I'm ready for this one. And if you want to be ready for this one as well, check out this video, check out the description section down below. You can download the PDF of this thing, and you can also check out the timestamps of every single part. Sorry, I was thinking about what I want to say. Check out the timestamps of everything I'm going to do with you. I'm going to do the lecture portion first, and then I'm going to do the problem set, which goes up to, I can't remember, 50 some odd problems, something like that. So we'll see how long this video goes, and without further ado, let's go ahead and get started. Oh, grab a calculator for this one, and I'll just mention, because it doesn't say it on here. It says previous terms to know are rhombus and kite. There are many more terms to know than that, or processes. You got to know your special right triangles, 35, 45, 45, 90, and 30, 60, 90. You got to know your trig, sine, cosine, and tangent, if this section is what I believe it's supposed to be. So, we're going to find areas, oh, I didn't even know this. We're going to find areas of rhombuses and kites. We're going to find angle measures in regular polygons and find areas of regular polygons. This stuff requires that you know some of the trig and 30, 60, 90 triangles, 45, 45, 90 triangles. New core vocabulary: center, radius, and apothem, and central angle of a regular polygon. We've heard of center and radius and central angle of a circle. Regular polygons also have those. Apothem's a brand new word for us. We don't say apothem. We say apothem. All right. Finding areas of rhombuses and kites. Kind of an interesting bit where this is being just thrown into the mix. I guess that's why they're calling this section areas of polygons and not just regular polygons. But okay. You can divide a rhombus or kite with diagonals D1 and D2 into two congruent triangles with base D1. So I got a base D1 right here. This is my base D1. Then we'll have two different congruent triangles here and here. Oh, height, 1/2 of D2. So here's all of D2. Here's half of it and half of it. This is for rhombus specifically. And then the area is 1/2 base times height and base times height. And there are two of them. The area of the rhombus or kite is two of those, and you get 1/2 diagonal 1 times diagonal 2. Yeah, basically, like the way that I would generally say to students of the past is it's basically a rectangle divided into 4 subquadrants, and each of these subquadrants right here, or these quadrants, these sub areas, are each divided into 2 when it comes to those areas as an overall, right? This triangle is half of this whole area. This triangle is half of this whole area. So it's half of all the areas of D1 times D2, and so that's what we get there. Now, a kite has the similar thing. Area of rhombus or kite is this general bit. That's if you see them as, because rhombuses always have perpendicular diagonals, so do kites. So if you see it kind of in that fashion with the diagonals, you can definitely work it out. Rhombuses are also base times height because they're like a parallelogram, but we probably won't see them this way in this section. So they give you the formulas there. Let's take a look at some examples. Find the area of each rhombus or kite. Here we have a diagonal of 8 and a diagonal of 6. 1/2 of the diagonal 1 times diagonal 2 is half of 6 times 8. Half of 48 is 24 square meters. Part B, this diagonal, I don't know which one they're calling 1 and 2, but this diagonal is 10, this diagonal is 7. Half of diagonal 1 times diagonal 2, half of 70, would give you 35 square centimeters for that one. So that's the basic construct of what we're doing there. Okay. I forgot my picture's kind of in the way, so sorry if I cut off any of the text that you were looking at. All right, let's keep going forward. Finding angle measures in regular polygons. I think this is the crux of what this section's all about. This is what I was kind of talking about. That being said, I haven't talked about areas of those things in probably 9 years either. The diagram shows a regular polygon inscribed in a circle. So regular hexagon is here, and it's inscribed. The center of a regular polygon and radius of a regular polygon are the center and radius of its circumscribed circle. So in circle P, that's P is the center, And also, because this polygon's inscribed in it, because it's a regular one, it also has what's called a center. It is equidistant to all of the endpoints and equidistant to all of the sides. And we're going to come up with those names, such as radius. Radius of the circle is also the radius of the regular polygon. It's the distance from the center of the regular polygon to any vertex. Boom, like M, to all vertices like that. The distance from the center to any side of a regular polygon is called the apothem. Now, generally, they drew it up here. Generally, you're going to see me draw it straight down right there. It's an altitude. It does bisect this side of a regular polygon, and it's the shortest distance to there. Now, a circle doesn't quite have that distance. As you can tell, it just goes to that side. To a circle, that doesn't mean very much, outside of what we've seen from a radius intersecting a chord. But even then, it doesn't go all the way down. The apothem is the height to the base of an isosceles triangle with two radii as its legs. So let's say I had these two sides right here. They'd be congruent, make some isosceles. And they have it up here. And then down there, boom, it's an altitude like that. The word apothem refers to a segment as well as a length. For a given regular polygon, think of an apothem as a segment and the apothem as a length. Oh, okay. True. A central angle of a regular polygon is an angle formed by two radii drawn to consecutive vertices of the polygon. So this is an example of a central angle of the polygon here. We've seen central angles of circles, but they can literally be anything because a circle has just infinite number of points. The points that we're going to refer to here are these vertices, things stemmed from the radii. So the central angles will be very specific to every type of regular polygon we're talking about. A regular hexagon has a specific central angle measure. To find the measure of each central angle, divide 360 by the number of sides. So a regular hexagon would have a 60-degree central angle because that's 360 divided by 6. A lot of what we're going to do there. And that apothem will also bisect the central angle. A lot of big things you're going to be seeing from that. Okay, finding angle measures in a regular polygon. Now, interestingly enough, wait, hold on. I want to see which ones they're talking about. AFB, AFG, and GAF. Okay. If they were talking about interior angle measures, you would have done that in IM1, I assume. And it doesn't look like they're going to get that deep into the whole 180 times n minus 2 stuff. We're going to talk about the central angles here. So, in the diagram, ABCDE is a regular pentagon inscribed in circle F. Find each angle measure. We have the measure of angle AFB. First of all, that's the central angle. We're going to divide 360 by 5 to get the central angle measure, which is 72 degrees. Then they say find the measure of AFG. That's just this one right here, the double arc marked one I'm doing. AFG will be half of that because it's bisected. The apothem of the isosceles triangle bisecting it means you divide 72 by 2 and you get 36 degrees. That'll be a very common thing that we do. Find the central angle, divide it by 2 with the apothem. And then by the triangle sum theorem, we have a 90-degree angle, and then this 36. 36 and this acute angle right here that we got to find, add to 90. So 90 minus 36 gives you 54. So the third one is 54 degrees, measure of angle GAF. So I don't know if they're going to ask you to just find those individual angle measures, but we're going to use those individual angle measures very, very often to find things. Specifically, very specifically, the central angle and half of it. Finding areas of regular polygons. Here's where it all comes into play. There's a formula. You can find the area of any regular n-gon by dividing it into congruent triangles. This is exactly how I would prove it as well. If you wanted to find the area of this one individual triangle, you would do 1/2 base times height, S times A. S is the side length, A is the apothem. So 1/2 S times A is the number, is the area of that one triangle. And how many congruent triangles are there in this thing? Depends on how many sides there are. A 6-sided shape would have 6 triangles. 1, 2, 3, 4, 5, 6. Boom, 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 boom. So you'd multiply by 6. If there are 8 sides, though, you'd multiply by 8. But what we do instead here, I mean, that's what you do. So, but instead of making that formula look a little wonky and say, find the area of this, we kind of condense it a little bit more. They reassociate, and this is what I would do, they reassociate the 1/2 apothem here, this length, times, and take a look at this. They associate n times s. Now, s is the side length of each, is the length of each side of the regular polygon. They're all the same. N is the number of sides of the regular polygon. What happens when you multiply each side length by the number of sides of a regular polygon? You get its perimeter. You get its perimeter. And that's what they're writing here. I normally use a lowercase p when I write it out. But the area, probably incorrectly, but the area of your regular polygon is 1/2 apothem times perimeter. They also associate it with the n times s right there. But you'll hear me say area is 1/2 apothem times perimeter. So that's what you need to find. Find the perimeter of your polygon, find the apothem of your polygon. You get those two things, you'll get your area. So finding the area of a regular polygon, let's see an example. A regular nonagon is inscribed in a circle with a radius of 4 units. Find the area. So we have to find two things. We have to find the apothem and the perimeter. Now they require a little bit to do here. Okay. First things first. Well, I don't know which one they're going to find first, but first things first, a perimeter is found if you can determine the number of sides, 9, and then the length of each side. The length of each side here is determined based off this 4, this being a right triangle, and this being a nonagon. A nonagon has a very specific central angle measure. This is 360 degrees divided by 9 gives you 40 degrees for a central angle. But when you draw the apothem, it bisects that and it becomes a 20-degree angle. So right here, you see just a single drawing. You're going to see me do a lot of downward drawings like this. This single angle is 20 degrees, which means you have a right triangle with a 20-degree angle, and you have 4 as the hypotenuse. This is where trig comes in. If you want to find a whole side length, you got to find this individual part first. I could call it x. They call it mk in this case. And then you double it because it's bisected, and then you get an entire side length. So we're going to use sine for that. Sine of 20 is this unknown, if I call it x or mk, over 4. And then you multiply both sides by 4, and you get this. Now, leave it exact for as long as you can, because that's a rounded value, and you do not want to, or if you write it, you'd be rounding it. You do not want to round a value early. But this is the length of half of a side. If you double it, you'll get 8 times sine of 20. I'm sure they have it somewhere. Here it is. They get 8 times sine of 20 as a whole side length, entire side length. If you want to get the perimeter, you're going to have to multiply 8 times sine of 20 by number of sides 9, and you get 72 times sine of 20. I don't see that here. I see that here, but I don't see them actually get the exact, so we'll deal with it. Now, the apothem, this guy right here, L to M, you could find using cosine. Cosine of 20 is the apothem over 4. I'll just use the letter A in those cases. So you multiply by 4. Apothem is 4 times cosine of 20. So how do we find the area? It's 1/2 apothem times perimeter. NS is perimeter. Apothem is 4 times cosine 20. Perimeter is 72 times sine of 20. Multiply all that together, round to the nearest tenth it looks like they're doing, and you get 46.3 square units. That's a lot to do for a problem. That's probably the most you'll generally do for a problem. Normally, maybe they'd give you one of them, or maybe they practice you early on. But that's a big, bulky example of how to do this. Quite a bit of things. Just keep in mind what you got to find and how the apothem affects your polygon. It bisects both the side and the angle, and you got to find that central angle. Use trig, know the formula, go the rest of the way. Quite a bit. It's quite an ordeal. Okay, that's why I said I think that's going to be the heavy bulk of this set, what we're going to do. Finding the area of a regular polygon, well, we just saw that. Here's a word problem, though. You're decorating the top of a table by covering it with small ceramic tiles. The tabletop is a regular octagon, 8 sides, with 15-inch sides, and a radius of about 19.6 inches. What is the area you're covering? So this one should be slightly easier because this time you have the side length. You have the side length here. And there's actually more than one way you can find this apothem being given that side length. I don't think they need to give you this radius. They don't need to give you the radius. So let's see which way they go about finding it, because there's more than one way. But the perimeter should be simple, 15 times 8. So perimeter is 15 times 8, it's 120 inches. You get that. We still need to get the apothem, which ideally would be here. Here's why I said that there's more than one way to do this. Let's see what they do. They probably go, Pythagorean theorem. So 15 is everywhere. It's here, and it's all the length of PQ as well. That's all 15. Because an apothem bisects any side length, then half of that is going to be 7.5, which means if you want to find this apothem, you can use Pythagorean theorem. Apothem squared plus 7.5 squared equals 19.6 squared. So you can use that, and it looks like they're, do not round this early, by the way. They're just saying this is about the apothem's length, but notice that they use the exact value in the calculation. Thank goodness. And they're going to do 1/2 apothem times perimeter. Now, I said there's more than one way they could have found the apothem. You already know it's a regular octagon, so you can divide 360 by 8 and get 45 degrees. That would be the entire central angle. Half of 45 is 22.5. That would just be this angle here. And then you could use trig, sine, with this 19.6 and get that 7.5 value as well. Excuse me, cosine. You want to get this value. Cosine, get the apothem value, the 19.6. Either way, you'll get around that 18.108 value, and it works. It's more monitoring progress stuff. I'll leave it to it. So there's quite a bit that you can do there, and that will be the end of the lecture portion. So I assume we're going to start with rhombus and kite stuff when we actually get into it, but otherwise get ready for a lot of that regular polygon stuff. You have to know your trig. We didn't run into, by the way, any special right triangles yet, the 36, 90, 45, 45, 90. But if we do, I can skip the trig by using the 1-to-1 to root 2 relationship, the 1-to-2 to root 3 ratio relationship. So if you know those, great. If you don't, not so great. You actually might run into trouble. Okay? So make sure you have background for that stuff. So let's start with the vocabulary and core concept check. Explain how to find the measure of a central angle of a regular polygon. You divide 360 by the number of sides. So regular polygon, like a 5-sided shape, you divide 360 by 5. There are 5 central angles. They're each congruent, 72 degrees, things like that. Different words, same question. Which is different? Find both answers. Find the radius of circle F. Find here's a diagram. I didn't know. Radius of circle F. Okay, if this is like some A thing. Here's the radius of the circle is any of these guys right here. Technically, it's anywhere that goes to the circle, but any of the ones that go to here. Like when they said find AF, that's the length of AF, and that's the same thing. The length of AF is also the radius of circle F. It's also the radius of the regular pentagon. That's this one here. Find the radius of polygon ABCDE. That's assuming this is a regular polygon. They don't say it. But since they're saying apothem and such and radius, then I guess it has to be. Find the apothem. That would be different. That would be like this F to G, for example. That is not the same length as the radius. That's not the same segment as it would be. B would be different in there. So both answers, radius is those 3, and then apothem is that one. All right, guys, we're going to go and get started with the problem set. So go ahead and get this thing downloaded and get your please get your calculators ready. We're going to have to do a lot of things there. So we're going to go ahead, y'all, and get started. Let's start with numbers 3 through 6. Where we are going to find, hold on, I'm trying to move this. Now I just lost some screen here. Give me 1 second. There we go, it just blackened out on me. Find the area of the kite or rhombus. Change to black. Okay, number 3. With that diagram, let's say, so the area of a kite has perpendicular diagonals, and our area is 1/2 the product of your 2 diagonals. In this case, I mean, this is going to be true for all kites and all rhombuses. Rhombuses. So the D sub 1 here can be 19, and D sub 2 can be 38, for example, right? So the area will be half of 19 times 38. This is where you could possibly whip out the calculator, but this should also be 361 square units. Try and put square units each time that they don't have something represented. I feel like this is the time that we really ought to start doing that. They're eventually probably going to throw those in with word problems. Anyway, how do I do that so fast? Because half of 38 is 19, and 19 squared is 361, if you know. Okay, number 4, perpendicular diagonals for this here kite as well. And this time they have individual portions of this. So you can say D1 can be like 6 plus 6, 12. And D2 is 2 plus 10, which is 12. So we're going to be doing area of that as half of 12 times 12. Now 12 squared is 144, half of that is 72. So we'll get 72 square units for number 4. Numbers 5 and 6 look like rhombuses based on the congruent sides, but that does not change our formula, especially the way that they have this constructed. Number 5, we can do D sub 1 as 5 plus 5 as being 10, D sub 2 as 7 plus 7 being 14. And rhombuses bisect each other, by the way, in case you were wondering. So area is half of 10 times 14. Half of 14 is 7, or 10 times 7 is 70. So 70 square units for that guy. And then number 6, this one's a little bit different where I might, give me 1 sec, I might copy paste this one, and then I'll drag that number 6 part circle over. Because this time they give you one of the side lengths, and that's not one of the diagonals, right? So we're going to have to find the other diagonal by understanding some things about the properties here. Number 6. This 6, diagonals bisected in a rhombus, so that means these two are congruent to each other, which means each of these are 3, and these are congruent as well to each other as this is perpendicular. If you use Pythagorean theorem or know your Pythagorean triples, you'll actually find out these are 4. So, 3 squared plus 4 squared is 5 squared, so I'll live off that. These two 4s make 8, so if one diagonal is 6 and the other diagonal is 8, then we can work off that. The area is half of 6 times 8. Half of 48 is 24. Okay. So there's your kites and rhombuses and such. And like I said, I was kind of surprised it showed up here. I figured it probably would have been back in like chapter 7 when we actually did quadrilateral stuff. Okay, in 7 through 10, we're going to use the diagram. Now, they don't say regular polygon, but just like the first problem thing that we saw before from the vocabulary and core concept check, I guess we're just assuming it's a regular polygon. It is inscribed in the quadrilateral, in the circle, excuse me. But we're just going to have to assume it's regular from what they say. They ask what's the radius and stuff like that. So, yeah, it's all good. Okay, so let me just bring this figure over and see what we got to talk about. Numbers 7, 8, and 9. Let me hide that bugger of a... No. Sorry, a little OCD. Okay. Number 7, identify the center of polygon JKLMN. The center of the regular polygon is the same as the center of the circle. It is P. Center equals P. Number 8, identify a central angle of polygon JKLMN. I don't know if they mean central angle measure or just a central angle angle. Actually, they kind of told us from the section thing before. They said a central angle... No, they talk about the apothem, right? They said an apothem is one of the segments, whereas the apothem is the length. So for a central angle, I assume they're referring to just a name. I want to put colons here, not equals. Central angle could be angle NPM. Now, for the sake of covering myself, just in case I didn't get the value itself, the measure of angle NPM, y'all, it's a pentagon, so we divide 360 degrees by 5 to get 72 degrees. I believe this is what they were looking for, but just in case, I'm going to provide that as well. And number 9, what is the radius of polygon JKLMN? They're asking for the length in that case, not just a segment. Whereas a radius would be PN, or a radius would be PM, but the length in this case is consistent throughout. It'll be 5. So radius... This is where I'm going to put equals 5. Number 10, what is the apothem of polygon JKLMN? Again, they're asking for a length there. So I believe for the central angle, they just wanted a name, but it's good to get that practice in. So apothem, which I'll be using lowercase a here on out to describe that, is, I believe they're pointing to this guy. That's not the angle measure. So 4.05. We don't really have to do any work on that. They want to make sure you know where these things will exist. Now, whenever I draw these for myself, y'all, I'm going to be putting this stuff on the bottom shape, the bottom side of any shape that we have. So I think it'll make it easier for you to perceive. All right, give me a moment. All right, numbers 11 through 14. So they're really building slowly through these for you guys, so you can always make sense of it. So that first one, this central angle here, I don't think we did need that because they're going to ask you for it next, it looks like. Find the measure of a central angle of a regular polygon with the given number of sides. Round answers to the nearest tenth of a degree if necessary. So 10 sides, we're going to be doing 360 divided by 10, which is 36 degrees. That is number 11. So I don't have to draw anything, just the central angle. There are 10 central angles in a decagon, and they're all congruent, and they add to 360 like central angles would in a circle. Number 12, we have 18 sides. We're going to be doing 360 divided by 18. 36 divided by 18 is 2. 360 divided by 18 is 20. We get 20 degrees. No rounding necessary there. Number 13, 24 sides. I like quick problems. 360 divided by 24. I think that's 15. 15 degrees. And then number 14, 7 sides. I'm sure I have to round here, and I'm sure I have to look in the calculator. I have a theory. 7 sides, that is a heptagon. 360 divided by 7. Now, whoops, not 3. Now, 350 divided by 7 is 50, right? 357 is 51. 357 with a remainder of 3. 3/7 is around 0.42, so I'm going to guess it's around 51.4 degrees. I'm going to go use the calculator and figure that out right now. Pop up my calculator for the first time here. 360 divided by 7. Yeah, 51.4 degrees. So, 51.43. My bad. Excuse me. Okay. So that's still going to be that answer rounded to the nearest tenth. And it seems like on these they are rounding to the nearest tenth. If you remember on the previous sections, we were doing a lot of nearest hundredth, 2 decimal places. Not so much here. Okay, that's 11 through 14. Nice quick set, but of course we're going to slow down soon at some point when we have to do actual areas. Number 15, or numbers 15 through 18, find the given angle measure for regular octagon A, B, C, D, E, F, G, H. So they're going to ask for very specific ones within here. Maybe I can copy paste this guy over and see exactly what they want. Because all of these might apply to future problems where we do these things here, or depending on what they give you as angles. So number 15 is measure of angle GH, or GJH. GJH. GJH is this central angle, because those are 2 radii constructed for the octagon. So that's 360 over 8. It's octagon, right? Yes. 45 degrees. Number 16 is measure of angle GJK. GJK is this angle right here. It is, the JK is an apothem of this thing. It's bisecting this angle that we found from 45 degrees. So measure of angle GJK, you have to divide GJH by 2. Divide 45 by 2. That's 22.5 degrees, which is an angle measure we'd be using for finding area of the polygon or something that we might need for that. Number 17, measure of angle KGJ. Now you can use, just like I used in 16, you can use a previous problem to get you this problem. We just found out that this is 22.5 degrees right here. And this is a right triangle. So in this right triangle, if I want to find this angle here, KGJ, I can do 90 minus 22.5 because acute angles are complementary in a right triangle. So 90 minus 22.5, which is 67.5 degrees. I probably will use that one less often, or I would probably obtain it in a different way if you know how to find the measure of an interior angle of a regular polygon. Maybe. It depends on which one would be faster in that case. But generally, I don't need to find that one if I have the central angle bisected. Number 18, measure of angle EJH. Now, I'll be honest, it's unlikely you're going to be doing a lot with an angle like this when it comes to finding areas of polygons, but they're trying to see if you know what's going on within this figure, I suppose. So EJH, take a look. This is a radius, this is a radius, this is a radius, this is a radius. You have 1, 2, 3 congruent triangles with all 3 central angles being 45 degrees. So measure of angle EJH is 3 times 45, which is 135 degrees. So that makes up 3/8 of your entire circle, regular polygon. Okay, let's go to exercises 19 to 24. We are now finding areas of regular polygons, and they are drawn for us. So, a regular or equilateral triangle, they give you a side length, they give you the apothem. As you can see, this dot there, that represents the center. This center is, again, equidistant to all sides and all vertices of your polygon, meaning here's another apothem, here's another apothem, and then here's a radius and a radius and a radius. Now, we don't need all those things. In fact, I'm not going to use any of them except for one of the, no, actually, I don't even need that. Here's all we need. We just need these 2 numbers here. The area of a regular polygon is 1/2 apothem times perimeter. There are other ways to find areas of triangles, but given what we have here, I guess I'll leave it like this. But if you want me to double check and show you that it works, we can. Like as in the information we would know. Anyway, area is 1/2 apothem times perimeter. Apothem, let me write this. Apothem is 2√3. Your perimeter is 12 times 3. It is a regular polygon after all, equilateral, so we get 36 units there. So your apothem in this case is 1/2. Your area is 1/2 apothem times perimeter. Half of 2 is 1, and 36 times root 3 is 36 root 3. Square units, that's exact. Of course, I'm sure rounding is something they're going to want. They've been doing the nearest tenth. So let's figure out 36 times the square root of 3. 62.35, so around 62.4 square units. I'll probably box the rounding ones here from here on out. Here's what I want to show you as well, though. What do you know about equilateral triangles? 60-degree angles, right? That means if I drew a full side here, full altitude, let's ignore this for a moment, then this would be a 30, 60, 90 triangle right there. In a 30, 60, 90 triangle, and this is build up for something we might have to use later, hypotenuse is twice as long as the shortest side, so this would be 6, and this would be 6 root 3. Well, the area of a triangle in general is 1/2 base times height. So this would be 1/2 of base 6 times 6 plus 2. 6 plus 6, or 6 times 2 is 12, times the height of 6 root 3. 1/2 of 12 is 6. 6 times 6 root 3 is 36 root 3. So you still get the same answer regardless using a different format of that. It's just that on other regular polygons, you don't have such a luxury. This kind of confirms that that works out in its own way, using other things and reminding you of how 30, 60, 90 triangles work. Okay, number 20. That's a regular I don't know. I have to count. Looks like an odd number, probably 9. 3, 4, 5, 6, 7, 8, 9. Regular nonagon. So we have, once again, a side length. Okay, we don't have apothem, but the perimeter is going to be 6.84 times 9. And this will be an exact value, which is probably not an integer. 6.84 times 9. We get 61.56. Keep that in our back pocket. Here's what I'm going to do, and I'm going to generally do this a lot. I'm not going to copy over the diagram. What I'm going to do instead is pretend like we have this whole... I'm just going to draw this section of my shape with this center, if that makes sense. I'm just going to draw the bottom portion of this and say, hey, it's a 9-sided shape. We know that, all this stuff. And information that we have here, we have the radius. And the radius is 10. We have to find the apothem. We have to find this guy right here, A, given what we would know about a nonagon's central angle measure. A nonagon central angle measure here. Trying to just move it out of the way. There we go. Okay, so to find apothem, we have to find the central angle, and the central angle is 360 over 9, which is 40 degrees. And half of 40 is 20 degrees. That makes this guy here 20. So to find A, the apothem, we're going to set up a trig equation. The cosine of 20 degrees equals the apothem over 10. So the apothem is 10 times the cosine of 20 degrees. That's exact. We have a perimeter of 61.56, an apothem of 10 times the cosine of 20. That is our setup to solve. So the area of this nonagon is 1/2 apothem times perimeter. And we're going to go and round that. Normally I'd actually write an exact full answer first before doing this. Probably easier for me in the calculator. But oh, by the way, make sure you're in degrees in your calculator. I don't know what 61.56 is going to do with these things. So here's what I'm going to type. You know, half of 10 is 5. So I'll do 5 times cosine of 20 times 61.56. And that was an exact value. So we get, and am I in degrees? Yes, I am. Degrees. So this is 289.2 square units. And that's our answer for the nonagon. So I'll try and speed up through some of those a little bit more. I'm still going to do the same concept of drawing if need be, and for the most part we will. Let's go to number 21, where we have a 1, 2, 3, 4, 5, 6, 7. By the way, I'm going to do this for each problem as well. I'm going to state how many sides there are. So this was n equals 9, right? This is an n equals 7 sides on this one. Now, we did 360, 51.4 degrees. I'm going to get an exact value for this thing, by the way, though. I got to think if I need it. I don't. I don't need... I need 7 for the, not for trig. I'm not going to use central angles this time. We have this part of this drawing where we do have the apothem of 2.5. That is A. We need to find the perimeter. So to find the perimeter, we need to find a side length and then multiply it by 7. Now 2.77, we got to assume that that's going to be as exact as they give us. We just got to find this little x guy and then double it to find a side length and then multiply by the perimeter. So, or multiply by 7 to get the perimeter. So let's start with x squared plus 2.5 squared equals 2.77 squared. And I'm actually thankful that they did that for us with the heptagon, because that would have otherwise been a rounded angle measure value, and then we got to work off that. Not to say we're not going to have to round here, but this is x squared plus 6.25 equals, let's see what 2.77 squared is. 7.6729. Let's subtract 6.25, and we get 1.4229. 1.4229. So x is the square root of that value, right? X squared is that whole thing. Take the square root of it after subtracting it over. Let me make sure that the square root of that's not an exact answer. It's not. But I did take its square root in my calculator. I'm going to have that number in mind. I'll probably just write it out again later when it comes to like everything that we do with it, because that's half of a side length, right? Half of a side length. So let's go back to that. 2x is a full side length, so this is 2 times square root of 1.4229. So the perimeter is 7 times 2 root 1.4229, or 14 root 1.4229. So let's leave it exact. So we have an apothem of 2.5, a perimeter of 14 root 1.4229. The area of this regular heptagon is 1/2 apothem times perimeter. And remember, all this is exact still based on what we have. Half of 14 is 7. 7 times 2.5 is 17.5. I kind of want to write that first. 17.5 root 1.4229. I believe that's right. So that's square units, but I'm going to go ahead and actually use that in the calculator. So times square root 1.4229. Okay, we get 20.87, so around 20.9. 20.9 square units, area of that regular heptagon. And then number 22, we only have a side length of 7 in this regular hexagon. So this time I believe we're going to have to work a little bit more on the kind of trig aspect of this. So n is 6. S, I guess, the side length. Well, I'll just say P. P is 7 times 6, which is 42 units. So we got to find the apothem. In order for me to find the apothem in this guy, again, this is how I'm just going to draw the bottom part of this. We're going to do the following. We have 7 as an entire length, so 3.5 will be half of that. Okay? We got half of that is 3.5. And this is a, what do you call it? Hexagon. 360 divided by 6 is 60. Half of that is 30. So 30 is half of a central angle measure that goes here. This is a 30, 60, 90 triangle. To find the apothem, you don't need trig. This can be 3.5 root 3. It's a 1 to 1, excuse me, it's a 1 to 2 to root 3 ratio relationship, like this length is 7 as well in this hexagon, by the way. But I don't need that. I just need the apothem of 3.5 root 3. So A equals 3.5 root 3, and we have our values, 42 and 3.5 root 3. Area is 1/2 apothem times perimeter. Half of 42 is 21. 21 times 3.5 is 73.5, I think. Let's see. Times 3. Whoops, I did not finish that. 3.5. 73.5. So 73.5 root 3 square units is an exact answer. And rounded, we get 127.3. 127.3 square units. And there we go on 22. All right, we have two more in this set. They are not drawn, and that's perfectly okay because they give us the shape name that gives us number of sides. They tell us by detail what things are. I might do that bottom part drawing. By might, I mean I will, unless they give us everything. An octagon with radius of 11. So if the radius is 11 in this scenario, that's this right here. We have a right triangle. An octagon is a 360 over 8 being 45 degree central angle measure. Half of that is 22.5 degrees. So 22.5 degrees exists here. We need to find this length and this length with that information in the regular octagon. We're going to have to use trig. So for apothem, we can set up the cosine of 22.5 to be a over 11. So a will be 11 times the cosine of 22.5. Let's keep that exact. And listen, x is used sine. Sine of 22.5 is x over 11, so x is 11 times the sine of 22.5. Now that is half of a side length. So if we double that, we get 22 times the sine of 22.5 degrees. And therefore the perimeter will be 8 times that value. So that'll be 176 times the sine of 22.5 degrees. So we have the perimeter here. We have the apothem here. Let's kind of box those so you know where they are. So we're going to do area as 1/2 apothem times perimeter. 1/2 apothem times perimeter. So I'm going to spare you guys the exact answer for this one just because I'll still have cosine and sine to deal with both together. So let's do, well, half of 176 is 88. So 88 times 11, I'm going to kind of just find my own faster way to write everything, times cosine of 22.5 times sine of 22.5. Hope I didn't screw anything up along the way. I got 342.23, so around 342.2 square units on this guy. Number 24. A pentagon with an apothem of 5 units. Okay. Pentagon. Apothem. Let's draw that bottom part again. Here's our apothem. A pentagon has a central angle of 72 degrees. When you divide that by 2, you get 36 degrees. So in this pentagon, we'll get 36 right here. We need to find this length, double it, and get the perimeter. So x is tangent. Tangent of 36 is x over 5. So x is 5 times the tangent of 36. Let's go faster this time. Perimeter, we're going to do 5 times double 5 times the tangent of 36, so 10 times tangent of 36, right? X is just half of this part, 2 of these, boom, doubled is 10, and then 5 number of sides is perimeter. So we have apothem of 5, perimeter of 50 times tangent of 36 degrees, and now we're going to be able to find the area with that. We'll do 1/2 apothem times perimeter. So I'll get you the exact one this time. Half of 50 is 25. 25 times 5 is 125 times tangent of 36. And I will compute that for y'all right now. 125 tangent of 36. And we get 90.8. 90.8 square units. So there we go. That time we used tangent for that. First time we got to see that one. And that is pentagon, that is area. So those are of the, I won't say basic types, those are the conventional types that you would see. Now that we're hitting error analysis, it's generally after that we do more word problems, modeling with mathematics, and proofs, and critical thinking. So those are probably the easiest of the kinds that you'll get before we hit something else on them. Number 25, error analysis. Describe and correct the error in finding the area of the kite. So I see a diagonal that would be a length of 4. This one would be a length of 8. And they decided to go off these things right here, the 3.6 and 5.4. Those are not diagonals. Those are actually sides. The fact that they are diagonal might be what someone might mistake themselves. Oh, that mess. They used side lengths of the kite and applied it to the formula which necessitates diagonal usage. It could be possible that they mistook diagonally constructed sides, diagonally appearing sides, for diagonals. See, diagonals are segments across non-adjacent vertices. This is a diagonal. It may be vertically drawn, but it is a diagonal. These diagonals here are perpendicular. So when we have to find this area, obviously correct the error. We've done a couple of these earlier on. So we're going to do 1/2 4 times 8. Right? 2 plus 2 is 4. 3 plus 5 is 8. And that'll be 16. 16 square units for that guy. I'm scared to see what the next one will be. All right, let's see. I want to see what kind of errors people... I don't remember. See, again, I haven't taught this for so long. I can't remember what kinds of errors people generally do. Maybe you'd lose your work somehow or just wouldn't know how to start. But what work might be mistaken? Describe and correct the error in finding the area of the regular hexagon. They first find a side length by doing the square root of 15 squared minus 13 squared. So let's say that this is S right here. I've been putting X. But if this is S... Pythagorean theorem would get you this far, and they said about 7.5. For me, I'd say an error is rounding early. Let me first make sure that it works that way. I'm guessing they didn't double that number, though. So 15 squared, oh, that's 225. 225 minus 169 and square root of that. So it's 7.48-ish. I'm getting this in the calculator here. So yes, it's around 7.5. That's all good. Let's see if they didn't double this value, though. So area is 1/2 apothem, 13, boom, times perimeter, 6 sides, and 6 times 7.5. Yes, that's the problem. So the problem is, and I'm going to call this an X instead. If we want to call the whole thing S, that's fine. And keep in mind, this was not an S, 5, this is an S. Okay, so that's an S. Their problem is, although proper math and all kind of rounding early kind of thing, I'm sure they used exact numbers. The side length, the calculations they made found only half of a side length, not the full length, which needs to be doubled. Now, if you double that, you get 15, but of course it is a rounded value, so I'm going to leave the exact value in there that I'm getting. So the X that we need to find in that situation will be the square root of 15 squared minus 13 squared, which is the square root of, I didn't come up with what just 225 minus 169 is, and I don't want to be wrong. 225 minus 169, 56. So square root of 56, or that is 2 root 14, I believe. 14, yeah. So 2 root 14 is that. Now, if I double that, that'll be an S, if you will. S is 2x, which is 4 root 14. So that's a side length, and I'm going to use that exact number when we do this. So area is going to be 1/2 our apothem times, perimeter, I didn't get that yet. Perimeter is 6 sides. My calculator's in the way. 1, 2, 3, 4, 5, 6. 6 sides. 24 root 14. All right, apothem times perimeter. Now, here's the thing. Whatever answer they got, I think this answer will be doubled. They got 292.5. I think we're going to get about 595. So, half of 13 times 24 root 14. 585, excuse me. So, this is a rounding early issue. 583.69, 583.7. So, okay, I'd say their other issue with this is they rounded early. That 7.5 is not to be trusted. Remember, it was more so 7.483314. That matters. That matters. You do not round those numbers early. So, I'm going to include that. They also rounded early. Even if you write out 7.5 here, just to kind of simplify your writing, use the exact number in your calculations, but try and do the simplifying radical stuff. Maybe they're going to ask for exact answers someday. All right, numbers 27 to 30. You throw a dart at the region shown. Your dart is equally likely to hit any point inside the region. Find the probability your dart lands in the shaded region. So the circle is your 100% chance of hitting, just the circle itself, the region. So the shaded regions we got to find. So we're going to have to take out areas of the inside parts or whatever's provided. Generally, they're inscribed regular pentagon, square, equilateral triangle, and then something else on the last one we're going to have to do. But we also have to find the probability. So you have to divide by the circle's area as well. So the area of the circle, well, I can't get that one yet because I need to find the radius. So let's start with this regular pentagon. Let's just construct some stuff here. The perimeter of the pentagon is going to be 12 times 5, which is 60. These are, by the way, these have units, so 60 inches. Now, as far as the rest of the drawing goes, we have, this is 12, so half of that will be 6. That'll matter for other things we do here. We do have to get this radius too, by the way. Keep that in mind. For the circle, we have to get the radius, r, and we need this apothem. Now, central angle of a pentagon we've seen to be 72 degrees, so this here is 36 degrees. So let's use the 36 degrees and trig with the 6 to get the radius and the apothem. Now, for apothem, we'll use tangent. So tangent of 36 degrees is 6 over the apothem. Switch places here, apothem is 6 over tangent of 36 degrees. So when it comes to the area of the pentagon, I'm ready to go on that one. For the circle, the radius, we're going to use sine. Sine of 36 is 6 over r. Sine of 36 degrees is 6 over r. Switch places there. R is 6 over sine of 36 degrees. Now the r is used for the area of the circle. So let's write some things out here. The area of the circle is pi r squared. And if you write this properly, 6 squared is 36, so I'll have 36 pi. And then on bottom, I'll have, they call it sine squared of 36 degrees, like that. You still square the sine of 36. Not the 36 itself, but just that. But that's how it will look. The area of the pentagon is 1/2 apothem. Where's apothem? 6 over tangent of 36 times perimeter, 60. So as an exact answer, half of 6 is 3. 3 times 60 is 180. So I get 180 over tangent of 36 degrees. So there are the two areas. To find the area of the shaded region, I have to do the area of the circle minus the area of the pentagon. So area of shaded is going to be 36 pi over sine squared of 36. I hope I didn't make a mistake along the way. Minus 180 over tangent of 36. And the probability of the entire thing is taking this divided by the area of the circle. So instead of writing area of shaded, let's go straight to probability of shaded. Probability of shaded, we take this and we divide by, 36. This is why it's good to actually clean some of this stuff up when you're calculating this stuff. Otherwise, it's going to be quite bad. Over sine squared of 36. I'm just going to write it kind of like that. So I'm going to type this in the calculator. Hopefully you can pause this and write this stuff down and then follow along with what I do in the calculator here. I'm going to pause and refill my drink. So, calculator. We're going to do parentheses. I'm going to clear that out. Parentheses. 36 pi. Assuming I didn't make any mistakes. Over. Sine of 36 needs to be squared. So in parentheses here, sine of 36 squared. Wait, I want to square, yes. That should work. Minus 180 over tangent of 36. Now I have to close this parentheses set as well. That'll give me my numerator. Well, let me just press enter on this. This is the area of the shaded region here on this problem. Now we're going to divide by the area of that entire circle. So if I didn't press enter beforehand, I would have hit divided by then and there with the parentheses involved. But let's divide that now by, in parentheses, well, actually, I don't know if this part probably doesn't need parentheses, but 36 pi over sine of 36 squared. So sine 36 squared. All right. 0.243, I don't know how many decimals we're going to need here. I think I used 5 decimal places in previous times. 24317. 24-ish% chance of that. It seems a little large. But keep in mind that's still a quarter of everything, and 5 of those all together, imagine that's the inside. I don't know. It still kind of seems a little large, but I'll take it for what it is. Right now I'm going to trust it. I'm going to pause and get water anyway. I can just go back and check on some of my stuff and see if I might have made any mistakes. I feel like it's good, so I'm just going to leave it. Anyway, so let me pause, and I'll come back. Okay, I'm back. I didn't look too hard at it. I'm just going to... It seems fine. I mean, if there's a problem, I don't even know where to inspect. That's a lot of things to change. It's probably in the calculator if there's a mistake, but that seems fine. That seems like a quarter of that whole thing. All right, number 28. And these are pretty drawn to scale too, so it's good to trust. Okay, so this is a square, right? It's a regular quadrilateral, it's a square, which is pretty big that we can work off here. First, what we do have is the radius, not just of the square, but of the circle. So the area of the circle in this case is pi times 14 squared. That's 196 pi square inches. And by the way, I don't know how much the units are going to matter because they're going to ask about probability, so we're going to divide those things later anyway. There's the area of the circle. That's what we'll divide out in the end. The area of the square, let's kind of come up with that thing. So in this one, we have a radius of 14, but a square has that 45, 45, 90 triangle ratio relationship. Sorry, they'll say 45 in there. So this is 14 over root 2. And listen, there are a lot of ways to find the area of a square, right? Oh, you know what else we can do? Hold on. We can totally do this. We can go... A square is also a rhombus. So that means all of these are 14. I'm just going to go the faster route, especially when they have it rotated like that. It just kind of reminded me of one. I was going to say, instead of redrawing it, these are all 14. It's a square. So the area of the square is the same as the area of a rhombus because a square is a rhombus. 1/2 d1, 28, times d2, 28. Half of 28 squared. I don't know what that is, though. So 14 times 28. Yeah, totally do that. 392. Don't get too stuck in just one way to do something, right? You can totally go about multiple ways. I mean, what I was going to say with the square was I wasn't going to do 1/2 apothem times perimeter. I was going to do the square of your side lengths. So once I found out one of the side lengths, I was just going to square it. But even still, this is even faster. So the probability of the shaded region, we're going to take the area of the circle minus the area of the square. Sorry. And divide it by the area of the circle. Like that. No, those don't cancel. You have to divide it. So in my calculator, this is a lot easier looking as far as numbers go. So I'm going to use parentheses, 196 pi minus 392. Now that would be the area of the shaded region. And let's divide by 196 pi. This needs to be in parentheses because that pi needs to multiply with 196. And here you'll get 0.36338. Again, as a probability, that's around 36%. I don't know how many decimal places you'll actually need, but I'm going to go ahead and use that many. So we're kind of in ballpark of what we're going to say. It was around 36%. Okay, let's go to number 29. Now, once again, if there's an easier way to go about finding the area of the equilateral triangle, let's do it. Otherwise, we can use any means necessary. So equilateral triangle with a radius of 8, that's also the radius for your circle. The area of our circle is going to be pi times 8 squared, or 64 pi. Square inches. All of these are square inches, or inches. With regard to the triangle, just draw the whole thing. With regard to the triangle, we have a radius of 8. I'll work off that as the hypotenuse of this. A triangle's central angle measures 360 over 3 is 120 degrees. So this is 60 degrees as half of that. That makes this a 30, 60, 90 triangle. 8 is the hypotenuse of this 30, 60, 90 triangle. So half of 8 is 4. And then this becomes 4 root 3 as half of one of the side lengths. So your apothem is 4 inches and your perimeter is 3 times 8 root 3. If we're going to just go about it the conventional way of doing the apothem times perimeter stuff. So 24 root 3 inches. So your area of your triangle is 1/2 apothem times perimeter. Half of 4 is 2 times 24 is 48. So you get 48 root 3 square inches. So as far as the probability of the shaded region, which is that outside part, probability of shaded, we're going to take the area of the circle minus the area of the triangle, the equilateral triangle, and divide it by the area of the circle. So I'll get 64 pi, I'll just do this one here now that you've seen one like it, minus 48 root 3, and I'm dividing that in parentheses there by 64 pi, also in parentheses, and I'm getting 0.58650. 58650, around 58-59%. So that's what we get there. All right, number 30. 30 is a little bit different in that it's only one portion of like a thing. This is also called the area, I believe it's called a segment. There's a sector, which is this entire thing, which we're going to use, by the way. We'll take the area of this sector and divide it by the area of the, subtract the area of the triangle. You could also recognize what kind of, given a 60-degree central angle, that it's a regular hexagon this would have been in, and you could divide the area of that bigger part by 6 or whatever. I'm just going to take this one individual part and go from there. So let's copy and paste this one over. I think there's, I think there's value in doing that. I'll just kind of have it enlarged and mark it up on this. So on this problem number 30, to find the area of a segment, again, we need to find the area of the whole sector, which would have been out of the previous section, and subtract the area of that triangle. So this is a 60-degree arc measure. So 60 out of 360, that's 1/6, is equal to, what are we trying to find? The area of the sector. I'll just call that X. I don't know what else to say. Area of the sector out of the area of the entire circle. Now, to find the area of the entire circle, there's still some stuff to do. Okay? So I haven't written that out yet. I just wanted to get that stuff set up. So let's see what to do. This 60-degree arc measure is also a 60-degree central angle, which means half of that is 30. So this is a 30, 60, 90 triangle. This 2 root 3 is the apothem, yes, but also we can get this length here in the 30, 60, 90. That would just be 2. You got to divide 2 root 3 by 2, or by root 3. And then double that here and you get 4. That is the radius of the circle. So for the area, we'll get pi times 4 squared. So x is going to be 1/6 of 16 pi. I've kind of seen that before, which is 8 pi over 3 square inches. This is the area of the sector. X equals area of sector. So we have the area of the sector. Now I need the area of the triangle. This is not an equilateral triangle. I could do, I guess, an apothem times perimeter thing, but I'm going to do 1/2 area of base times height. I'll make the apothem the height of the triangle. 2 of these 2's is a 4. That makes the base. So area of triangle is 1/2 base times height. Half of 4 is 2 times 2 is 4. We get 4 root 3 square inches. So when it comes to the area of the segment, I'll just write that out first. Area of the segment, we get the area of the sector, 8 pi over 3, minus 4 root 3. That's in square inches. I'll leave it like that even still. So the probability of that segment to be hit is this divided by the area of the circle, which is 16 pi. So the probability of the shaded equals 8 pi over 3 minus 4 root 3, all divided by 16 pi. Quite a bit, and you're still not out of the woods until you get it on the calculator, so let's go ahead and take a look at that. Let's do 8 pi over 3. I mean, practicing using a calculator with order of operations in parentheses and just knowing the nuances of it's very important, I'd say, especially if you're going to type it all in one fell swoop. And that's also why simplifying things can also be very helpful for you as well. So a very small number, and that's kind of what I expected as well, right? We're getting something, that segment is just one small portion of this entire thing with that angle. So this is going to be around 0.28, around 3%, 0.02. 0.02883. Around 3% is what we're looking at for that one, for probability. Okay, that's number 30. We still have quite a ways to go. I think we're going to number 52, right? So 31 and 32, we're going to be modeling with mathematics. Let's kind of get them in the shot. Basaltic columns. Oh, I thought that was a city landscape. Basaltic columns are geological formations that result from rapidly cooling lava. That's really cool. Giant's Causeway in Ireland contains many hexagonal basaltic columns. Suppose the top of one of the columns is in the shape of a regular hexagon with a radius of 8 inches. Find the area of the top of the column to the nearest square inch. This time I'm just going to draw out a regular hexagon. I actually have the tool. So this is the top of one of those basaltic columns. Okay, that's, just deal with it, right? It just is. It totally is. They said that the radius is 8 inches. So for this, we're talking about that 8 inches. I'm totally going to go the apothem route for this thing. They're saying find the area of the top of one of these nearest square inch. That's in inches. We got to find this apothem. We're going to have to find this side length to then find this, or this portion. To find this side length here, as these are congruent, and then find the perimeter. 8 in octagon. They said octagon, right? Oh, they said hexagon. Oh, I drew a hexagon. Perfect. I saw the 8 inches. Okay. Hexagon has a 60-degree central angle measure, and then divided by 2 is a 30-degree central angle measure. So we're in a 30, 60, 90 triangle. We don't have to use trig for that, because in a 30, 60, 90 triangle, this will be half of that, which is 4, and then the apothem will be 4 root 3. So in drawing that out, we kind of get all that information. So apothem's 4 root 3. Perimeter is going to be 6 times 8, right? This is 4, this is 4. So 48. So the area of this hexagon is going to be 1/2 apothem times perimeter. The exact answer will be 96 root 3 square inches. And rounded, we're going to get 166.3, about 166.3 square inches. Sorry, I have the little inches thing really close to the 166.3. Okay, did they say, because now it's a word problem, sometimes they say to the nearest square inch or whatever. I lost my page because I have to, anytime I go to the calculator, I have to flip off that portion. Oh, to the nearest square inch. Okay, so let me take out that 0.3. So good, now the space will look a little more appropriate. Or not, 166 square inches. Okay, number 32. Modeling with mathematics once more, or maybe more than this. A watch has a circular surface on a background that is a regular octagon. Where? I mean, I don't see the octagon in the thing, but okay. Has a circular surface on a background that's a regular octagon. Find the area of the octagon, then find the area of the silver border around the circular face. I need to make sure I know what they mean about where the regular octagon is. I'm looking at it, and I don't see what they're referring to. I see the 0.2 centimeter inch thickness here and 1 centimeter there. I can't tell. Let me pause and zoom in. So I can't tell which one's the regular octagon. I might have to get this from the actual official PDF and zoom in. Give me 1 second. Okay, how about that quality, huh? So I took this from the official PDF, not just that import. If I copied and pasted that, you've seen those images, they'd be blurry. That looks pretty good. Now I see the octagon. The octagon is this thing right here. It's the silver portion. So it's, let me highlight it because I couldn't tell from the other thing. It looks like a circle all to me, and I was not looking at that. I was looking at the white shape. This is the octagon here, basically. Okay. So there's a circular surface of the clock, of the watch, I should say. Circular surface on a background that is a regular octagon. Find the area of the octagon. So they measure out 1 centimeter in green, and then an additional 0.2 centimeters in red would ideally make the apothem of this. So let me do that on the bottom as well. I want to get a unique color, or at least thickness here. I wonder if this is going to be thick enough for us. That's the center. So down here is that same apothem length, and let me write that out in better terms. That's going to be 1.2. It's going to be tough to see, but 1.2 centimeters. Apothem is 1.2 centimeters of the octagon. What do they want? What do you want? Find the area of the octagon. Yeah, we have to find the area of this octagon. So apothem's 1.2 centimeters. When it comes to perimeter, we're going to have to do all the stuff with radius and such and such. So let me just even draw that part out. Not with the radius, but central angle. So 45, 360 divided by 8 is 45. So a central angle measure like that is going to be 22.5 degrees. That'll be half of the 45. So I need to find out perimeter by finding out this x, doubling it, and multiplying by 8. So, tangent. We can take tangent of 22.5 degrees and get x over 1.2. That's the centimeters of the apothem. So x is 1.2 times the tangent of 22.5 degrees. We double that to get 2.4 times the tangent. That's the side length. And the perimeter will be 8 times that. So perimeter is 8 times 2.4 times tangent of 22.5, which is 19.2 times tangent of 22.5, I hope. So your area of the octagon is 1/2 apothem times perimeter. Let's get an exact first. Let me get my calculator out. So half of that is 0.6 times 19.2. So 11.52. That's not the exact, but that's 11.52 times tangent of 22.5. Let me make sure 8 times 2.4 is that number. 8 times 2.4 is 19.2. Okay. So let's do 11.52 times the tangent of 22.5, be in degrees. I get 4.77. I've been using one decimal place, so around 4.8 square centimeters. That is the area of the octagon if I'm not taking out the circular surface portion. And I don't believe that we are, right? They just said find the area of the octagon. They didn't say the silver portion. Actually, I think that's the next question. The next question is then find the area of the silver border around the circular face. So I think we're taking out the circular face portion of that. The area of the circle, the radius of the circle is 1 centimeter. So the area of the circle is pi times 1 squared, so that's pi square centimeters. So I'm going to take that out. The area of the silver is, let's do that exact one again. It's good I still have that. 11.52 times the tangent of 22.5 minus pi. We take the circle portion out, that 3.14 bit. I'll do that in my calculator, minus pi, and I get 1.63. So around 1.6 square centimeters will be the area of just the silver portion, taking out the watch, the actual clock facing the circular portion there. Okay. Let's go to 33 to 35. Tell whether the statement is true or false. Explain your reasoning. True would have to mean always true, I suppose, in these scenarios. False, maybe I can just provide a counterexample. 33. The area of a regular n-gon of a fixed radius r increases as n increases. True. I want to try and get my explanation as to why. So, if you have a circle, a circle of radius r, just keep in mind, any regular polygon inscribed in the circle still is the same radius. A circle of radius r is the maximum amount of area you can get with that radius. The thing I mean by that is a square that's inscribed in the circle, for example, has less area. It has the same radius, but it has less area. It's just a square, right? Now, if I increase the number of sides here and I look at, say, an octagon with that, I don't know how to get this drawn perfectly in here, but an octagon inscribed inside the circle has more area than the square, but it's still less than the circle. I guess I didn't need to do an octagon, well, now that I'm rotated. Anyway, so hopefully you kind of see what my point is. As I increase the number of sides, I increase the area more slightly as it gets closer and closer to the circle's area, but the circle's area is the most as it can get, but it increases every single time. But true, and I'll just say circle's area, a circle maximizes the area, and a circle is like an infinite number of sides if you think of it like that. Not really, but it's like it approaching the infinite number of sides. So that works for me. Number 34. The apothem of a regular polygon is always less than the radius. True. This is because in a right triangle, just imagine this shot right here. Apothem is one of the legs of this right triangle, whereas the radius is the hypotenuse. Apothem equals leg of a right triangle. Radius equals hypotenuse. Hypotenuse always longer than leg in the same right triangle we're referring to. So true for that one. Number 35, I'm just going to assume has to be false. We only had 2 truths. Number 35, the radius of a regular polygon is always less than the side length. We've seen it more constantly. Or often. Wait a second. Yeah, no, false. Once you get more than a hexagon, I don't know if you saw that, but there was a hexagon where we saw side lengths of a regular hexagon, where we saw side lengths, I think, of 7. So it was like this, and they're like, hey, this is 7. So that means they're all 7. But in a regular hexagon, you actually have equilateral triangles. That means these are all 7 here. So less than, they're equal to now. So not always less than, that's a counterexample. Once you get smaller than this in a triangle, square, pentagon, all those regular, the radius is smaller than the side length. Once you get beyond the hexagon and beyond, it is not less than. Hexagon, regular, and beyond. That's going to be the new store instead of Bed Bath & Beyond. Hexagon and beyond does not meet criteria. I mean, you could do trig and stuff to figure that stuff out. You know, you get a central angle, you take the sine of the thing. There are a lot of things that we could do algebraically to show, hey, it's at this central angle measure, 60, at which this thing starts to break as well. But that's going to be false. Okay, number 36. False, because the other 2 answers were true, and they need us to do both. Number 36, reasoning. Predict which figure has the greatest area and has the least area. Explain your reasoning. Check by finding the area of each figure. So I'm supposed to predict first and then calculate them second. And these don't look drawn to scale. What, actually, do they? Does this 9? Let me just look at this first. Does this 9 look like it's... Oh, okay. These look kind of drawn to scale then. Are 2 of these 18? Okay, these look kind of drawn to scale. So let me go by the appearance of them to try and do the rest. I don't know if that's what they wanted me to do, but I will. That being said, I predict A has the least area and C has the greatest area just by visual, because these kind of look to scale. So least A, most C. That means B is in the middle. I don't even know if my visual appearance of that is correct. B may have more than C. Actually, now I'm questioning whether C has more or not. It just kind of looks bigger. I might be wrong. C might have the least. Just the way that a circle pans out, that circle might be like taking over more area right there than, you know what I mean? I have no idea. They might be exactly the same. They made up the problem. I haven't done it yet. So let's look at A's circle. The area is going to be pi times the radius squared. The radius is half of 13, which is 6.5. So pi r squared. Let's go straight to this. This is where you really do want to do like a rounding thing, because I don't know. One answer is going to be in terms of pi. One's going to have a radical. One's going to be exact. So you really want to have that here. So 6.5 squared times pi is going to be 132.7 square inches. And by the way, these are all in inches, I believe. I see A and C are. I'm blocked by the calculator with the rest of it. Part B, we're going to have to do a little more work on this one. So part B, we have a regular pentagon with a 9-inch side length. That means the perimeter's 45 inches, 9 times 5. This, we have to find the apothem. To find the apothem of this, we're going to take the 72-degree central angle that a pentagon has, 360 over 5, and divide that by 2 to get 36. 36-degree guy there, 9 inches broken up into 2 parts is 4.5 inches here. So the apothem is found by using trig. Tangent of 36 is 4.5 over A. So A is 4.5 over the tangent of 36 degrees. So that's your apothem. So your area is going to be 1/2 dat apothem. Whoops. 1/2 dat apothem times perimeter. I still don't know what it'll be until I calculate that. Half of 4.5 over tangent of 36 times perimeter. And I get 139.4. So 139.4 square inches. As far as a comparison between A and B, A is slightly smaller than B. So far B is leading, and so far my predictions are at least in order correct. We'll see where C compares. Hopefully C is largest by prediction, just by appearance. So for part C, we have to find the area of this region here. This isn't so much apothem perimeter stuff, really. In fact, I need to see, I believe that 18 must be just this. Just the way that it's aligned. It's not right in the center. They would show something else. So I believe that's the 18, whereas this part here, we'd be a little more uncertain. However, that's good. That's good, because an area of a triangle is 1/2 base times height. This isn't a matter of finding the area of this triangle and subtracting the area of that triangle. In fact, I don't know if I can really do that, because there's no angle measure, there's no length there. It's just 1/2 base times height. 15 is your height. 15 is your height. So the area of this guy, this will be really quick. That's 1/2 base times height. 9 times 15 is 135. Oh, that's in the middle. 135 square inches. Darn. So I was wrong. B had more than C. I know C looks bigger, but man, there's a lot cut out right there that this kind of fills out in a centrally kind of way. I did have pause with that, and I didn't realize these would be so close. So the order is actually from least to greatest, A, C, B. I was wrong. I was wrong. I was close. I had A as the least. All right. I'm sure most people would say that, though, too. And here's the thing. They were drawn to scale, so as long as you tell someone that, they eyeball it, I still think people will mostly say C. Here's the thing. You forget that this is part of the drawing, but if you omit it, I know I have to go to the next problem, but if you omit it, maybe suddenly it'll look like less area to you, right? Suddenly, that might look a little bigger. Maybe. All right. Let's go to number 37 using equations. Find the area. This is a graph. Find the area of a regular pentagon inscribed in a circle whose equation is given by x minus 4 squared plus y plus 2 squared equals 25. So here's the thing, and I've done a question not like this before. We did a circumference question, I think, or arc length, with a graphed circle. The center location doesn't mean anything. You need to know how graph things work, but the center location is 4, -2. That doesn't matter. The radius of the circle for x minus 4 squared plus y plus 2 squared, quantity squared, equals 25. The radius of the circle is based off this 25. R squared is 25, therefore R is 5. The radius of the circle is 5, and for what we're going to do, I don't need to graph this. I just needed the radius. We're done after that. The radius is 5. If a pentagon is inscribed inside of here, right, then you have, this look. That radius of the circle is also the radius of the pentagon. It said pentagon, right? Yeah, pentagon. So this length is 5 units like that. Now let's find the pentagon thing from that. So we've done quite a few of these. Central angle of a pentagon, this is 72. Half of that is 36. So we need to find apothem. We need to find this length to then find perimeter, all that kind of stuff, and we can find its area. So cosine of 36 is a over 5. So a is 5 times the cosine of 36. Sine of 36 is x over 5. So x is 5 times the sine of 36. I guess after you do so many of these trig things, it kind of pops up like that. So the perimeter, you have to double x to get 10 times sine of 36, and then multiply that by the number of sides, 5. So 5 times 10 times the sine of 36 is going to be 50 times the sine of 36. So your area of this pentagon is going to be 1/2 5 times cosine of 36. I feel like we've done these numbers before. Times 50 times sine of 36. I don't know if it was a pentagon that we did it for, but we did do 125 on this once. Let's see if this next number sounds familiar. Maybe it's not exactly the same. So half of 50 is 25. 5 times 25 is 125. And we have the cosine of 36 and sine of 36. Oopsie. Let me do that again. All right. Let's compute that one. So 125 times cosine of 36. It might have been a different polygon. 59.44. Yeah, I don't know if that number sounds familiar. But 59.4 square units for the pentagon inscribed in that circle. Who cares about the center? Number 38. What happens to the area of a kite if you double the length of one of the diagonals? If you double the length of both diagonals, justify your answer. Well, let's figure it out. So 38, if you have original area is 1/2 d1 times d2, and you double one of the diagonals like this, so double one of them, you get 1/2 2d1 times d2, which is d1 times d2. That's twice as much, twice as big in area. Now let's double both lengths of both diagonals. 1/2 2d1 times 2d2, doubling those. Half of 2 is 1 times 2 is 2. You get 2d1 times d2. Compared to the original, 4 times as big. 4 times as big. I don't know what to justify. That's it. I hope I didn't mess anything up, but that's all. Number 39. In exercises 39 and 40, write and solve an equation to find the indicated lengths, round decimal answers to the nearest tenth. The area of a kite is 324 square inches. One diagonal is twice as long as the other diagonal. Find the length of each diagonal. Okay, let's go back to our area. Area is 1/2 d1 times d2. Now our area is going to be 324. And let's say one diagonal is twice as long as the other. So d1 is twice as much as d2, something like that. So now I can re-express d1 in terms of d2 and just go off that. So 324 equals, instead of d1, I'll do 2 times d2 times d2. or 324 equals 2 times d2 squared. I know that looks weird. Let's put in parentheses if that helps. We're squaring that. Divide both sides by 2, you get 162. And take the square root of both sides, you get d2 is the square root of 162, which is 9 root 2. That's 81 times 2, and square root of 81 is 9. So 81, or 9 root 2 inches. What do they want? Find the length of each diagonal. So d2 is that. d1 is 2 d2s. So 2 times 9 root 2, and that's 18 root 2 inches. Now, they did ask us to round these to the nearest tenth. So 9 root 2 is 12.7, about 12.7 inches. And 18 root 2 is around 25.5 inches. Now notice, you're like, wait, isn't 12.7 doubled 25.4? Yes, but I'm using my exact values in my calculator here. And 25.45 rounds up to then 25.5. So for me, personally, I'd prefer going off of that, if that makes sense, when it comes to working that stuff out. Now, oh, you know what I didn't do? Hold on. I think I messed up this problem. Let me go back. So, despite all that stuff, I lost the 1/2 here. 1/2 that. So let's do that again. I'm just gonna undo everything there. Let's undo all that. 1/2 of that. I'm so sorry. I totally missed that. I was so focused on the d1 is this. So half of 2 is 1. So d2 times d2 is d2 squared. Okay, let's do that one more time. So square root, d2 is the square root of 324. What did I say before? 9 root 2? 324. Oh, that's 18. That's a perfect value. All right. That was much easier. So sincere apologies. d1 is 2 times 18, which is 36 inches. So nothing to round there. At least I got to speak on some rounding bits. At least I got to simplify some radicals. Totally missed that 1/2. I shan't do that again. All right, number 40. One diagonal of a rhombus, yes, is 4 times the length of the other diagonal. So if I have a rhombus, I know that shape is somewhere. I found it once. There it is. All right. One diagonal of a rhombus is 4 times the length of the other. I want to draw it to scale, see if this kind of works out. Boom. And I probably don't need the drawing because I can just do what I did last time, but I feel like a drawing. I want to remind you of what a rhombus is, man. Calls x and y, x and y. So y is 4 x's. How about that? I'm not going to use d1, d2. That's too weird on this stuff. It probably messed me up with that 1/2. The area of the rhombus is 98 square feet. So area of this rhombus, I'll make x be the whole thing and y be the whole thing there. So area is 1/2 x times y. All right, that's my d1 times d2. And the area here is 98. So 98 equals 1/2 of x times y, and y is 4x. So there you go. Half of 4x is 2x. 2x times x is 2x squared. So 98 is 2x squared. X squared is 49, and x is 7. 7 feet. Y, this is scattered writing, sorry. Y is 4 times 7, so y is 28 feet. Do they want the length? Yeah, length of each diagonal, so I'm getting 7 feet and 28 feet, and then I'm feeling kind of good about stuff with that. Okay, let's go to number 41, reasoning. The perimeter of a regular nonagon or ninegon is 18 inches. Is this enough information to find the area? If so, find the area. If not, explain why not. I think it's enough, yes. So n is 9, p is 18. Therefore, a side length, s, is 18 over 9, which is 2. And therefore, x is going to be 2 over 2, which is 1. What is x? In my nonagon, X is this, 1. Why does that help me find everything? I need to find the apothem. And to find the apothem, I need to have an central angle, and it's a nonagon. So 360 over 9 is 40, and 40 over 2 means this is 20 degrees. So I need to find apothem here by using trig. Tangent of 20 degrees is 1 over the apothem, so apothem is 1 over tangent of 20. So, I mean, I'm not explaining. Oh, it says, if so, find the area. It doesn't say explain how you can find it. So we're all good. So area of this nonagon, regular nonagon, is 1/2 apothem times perimeter. As an exact answer, look, 18 over 2 is 9. That's 9 over tangent of 20. So there is our area as an exact. Let's approximate that. 9 over tangent of 20. That is 24.7 square feet. Wait, is this feet? No, inches. The last one was feet, right? Did I put feet for these other numbers here? I did. I put. Okay, so that should be number 41. It should be true. And so you don't have to explain it if you can just show what it is. But my basic thing is once you have kind of one of the measures, they tell you to regular this and that. You can use central angles and such to find trig afterward. And I think that that's really the biggest thing that you have to just work off of, central angles. You have one side length off of that, even a radius, you're good. All right, number 42. Making an argument. Your friend claims it's possible to find the area of any rhombus if you only know the perimeter of the rhombus. Is your friend correct? Explain your reasoning. I'd say no, because rhombuses can change their size. It's not like a square, right? I can have a rhombus that can look like this and a rhombus that can look like this, and they can both be the same side lengths, right? They can both have lengths of x, but these are different areas. They're the same perimeter, but they're different areas. So no. No, you need more information such as an angle measure or a diagonal. Areas will vary if these change, even if the perimeter is constant. And that's exactly it. The perimeter is constant, not the area. Those would change. All right, number 43. We got a proof. We got a proof, folks. Prove that the area of any quadrilateral with perpendicular diagonals is A equals 1/2 D1 times D2, or D1 and D2 are the lengths of the diagonals. Well, I don't know if this was a purposeful drawing with that rectangle thing around it. The way that I would always say is that the area of this whole thing is D1 times D2, and when you break this up into their little quadrant sections, each of them is half of those areas. So this is half of the area of that whole thing. What the book did, though, as a section was they talked about these as like two different triangles. And they said, like, ignore the rectangle, actually. But what they I think the rectangle is just to show that D1 is this whole thing. What they said is two different triangles. Or they did it for rhombus. They said for the rhombus, no, I think they did it for the kite as well. They said the area of this triangle, we can do 1/2 base times height. And for this triangle, we can do 1/2 base times height. So, and then you add those together. So let's do this. Let's break it up like that. We have two different triangles. Let me copy and paste. Whoops, I just lost my answer there. Let me copy and paste this thing over. Because what I said out loud for my thing hopefully works. The area of those four individual triangles are half the areas of those individual rectangles. And when you add those all up, then you're good. Which we could do that. But let's just do them instead of 4 parts. Let's do them as 2 parts. Area of this triangle and area of this triangle. In order to do that, you can tell that D2 is the base of both of those. But these ones individually, let's call this like X and Y, because I have no idea how to put it otherwise. D1 is the sum of X and Y, right? Good to know. We're going to use that later, I'm sure. So the area of the top triangle, area of triangle PQR, is 1/2 base D2 times height of X. Okay? And then the area of triangle PSR is 1/2 that base, d2, times height of y. So the area of the rhombus, PQRS, can be expressed as the sum of both of those. 1/2 d2 times x plus 1/2 d2 times y. But if you factor out 1/2 d2 from both of these terms, you get 1/2 d2 times x plus y. This is where d sub 1 equals x plus y comes back in. That is 1/2 of d2 times d1, which is 1/2 d1 times d2. Multiplication is commutative, and we get that. And that's the area that we are versed in, right? That's the one that they're asking us to show. So finding the areas of triangles can get us there. And that's what I was saying with the other thing. You can do the areas of the 4 individual triangles, but I'd rather just do one set of them because they are still triangles. They still work based on height that way. And I think that works out just fine. All right, let's go to number 44 when they ask us, how do we see it? And they say, explain how to find the area of the regular hexagon by dividing the hexagon into equilateral triangles. Well, I kind of got into that a little bit when I mentioned that the hexagon, the radius and the side lengths are the same. But yeah, let's I mean, they don't have any whatchamacallums, any like variables or anything here. But yeah, these are all equilateral triangles, guys. Because the central angle of a regular hexagon is 60 degrees, and these are isosceles triangles always for all regular polygons, that makes the regular hexagon have equilateral triangles. And I know I didn't draw those perfectly, but just kind of deal with it. So yeah, these are all equilateral, so we all have x things here, right? All x's, yada, yada, yada. They're all the same. So if those are all x's there, it says by dividing into equilateral triangles. So that idea here is we're going to take the area of one of these times 6. So area of a triangle is something, and then the area of the hexagon is 6 times the area of that something. So if these are all x's here, actually let's do this. I want to take this as x. If this is x, then this is 2x, right? This is x root 3. I don't need the 2x. I'm just stating that this is a 30, 60, 90 triangle because that 60 is broken up into 30 there. So this is x root 3. Now, I'm not doing the apothem perimeter stuff. I'm just finding the area of that one triangle. If that's x, this whole thing is 2x. So the area of the triangle is 1/2 base times height. I think I did this on a previous problem, sort of, right? So that is x squared root 3. Hold on. Because half of 2x is x. So this is x squared root 3. Now the area of the hexagon as a whole is 6 times the area of the triangle, so area of the hexagon is 6x squared root 3. If x is half a side length, so x is half a side length. I know that's weird. If you wanted to get a full side length, what do they say? How to find the area of that? I didn't explain it, but that's the math of it. Just find the area of one of the triangles and multiply by 6. And that's all I'm going to say. Okay. All right, number 45, rewriting a formula. Rewrite the formula for the area of a rhombus for a special case of a square with side length s. Show that this is the same as the formula for the area of a square, a equals s squared. 45. A rhombus for the special case. What? Write the formula. Oh, okay. So they're saying they want to use the square as a regular quadrilateral. We did this, right? We did this on a problem. I did it kind of incidentally when I saw what was happening. Treat it more of the rhombus way. No, actually, no, I take it back. We're doing the opposite of. Remember when I had a square inscribed inside a circle and I said, let's use the rhombus formula. Let's do it the other way. Let's take the square. Rewrite the formula for area of a rhombus for the special case of a square with side length s. I'm trying to think if they want us to use the rhombus formula. I guess that's what. Well, you know what? Okay, fine. I will do it this way. The difference is we don't have any of the diagonal things, and last time we did. So we do have a square, and this is side length S. These are not 5s, but S's. Hopefully they kind of look like S's. So when we draw the diagonals of these, I'll line that up a little better. When we draw the diagonals of these, see the square does have a 45, 45, 90 triangle ratio relationship. So this is probably kind of what I was going to do last time. In a 45, 45, 90 triangle ratio relationship, this is S over root 2. I know it's S root 2 over 2, but we'll just leave it like that. S over root 2. So each diagonal 1 and diagonal 2 are going to be the same length. So S over root 2 times 2, which is 2S over root 2. I think I do want to simplify that, though. So that's, hold on, 2S over root 2. If you rationalize the denominator, that's 2S root 2 over 2, which is S root 2. So each, wait a minute. Oh, yeah, that makes sense. I was going to say, wait, that can't be longer, but it's the whole length. The whole length is S root 2. So the area, excuse me, of this is 1/2 D1 times D2. So this is 1/2 of S squared times root 2 is 2, and 1/2 times 2 is S squared. So that does go to show that area equals S squared is confirmed. Area of a square is a side times a side squared, and so it does tend to work out there using it that way. So that's similar to what we did do. The difference is we actually had to find the diagonal lengths doing special triangle stuff. So, okay, it's a different kind of problem. All right, number 46. Use the formula for the area of a regular polygon to show the area of an equilateral triangle can be found by using the formula A equals 1/4 S squared root 3, where S is the side length. Well, I was close to the hexagon one. See, this one said explain. Whoopsie. This one said explain on this one, and I used math for it, and I got this number here. This one's gonna be very close to that idea. Notice that x squared root 3 and s squared root 3. I guess they're gonna be kind of close to each other. 46. So same approach, but now it's a triangle. Equilateral triangle, mind you. Let's draw one. They said side length is S. What do they say? S is the side length. So in an equilateral triangle, I have a side length of, well, here's my center-ish. I have a side length of S. So when I draw radius kind of stuff like that, this is S over 2. S over 2. Now, equilateral triangle has a 120-degree central angle, so a 60-degree bisected central angle. In a 30, 60, 90 set, we have to find this apothem. Apothem is going to be root 3 times smaller than the leg opposite the long leg right here. So if I want to find the apothem, if I'm going to do 1/2 apothem times perimeter, right? They said use the formula for area of a regular polygon. Apothem is S over 2 times 1 over root 3. So that's S over 2 root 3. Let's probably simplify that because of the need for what we're going to do there. S, and remember that is an S, not a 5. 2 root 3 times root 3 over root 3 is S root 3 over 6. 2 root 3 times root 3 is 2 times 3, which is 6. So that's the apothem. So now, and the side length is S, so the perimeter, that's apothem. So the perimeter is 3S. Okay, area is 1/2 apothem, S root 3 over 6, times perimeter, 3S. This will be 3S root 3 over 12, S squared, S times S, 3S squared root 3 over 12, and 3 over 12 reduces to 1/4. So the area is S squared root 3 over 4. Is that what they put? They put 1/4. So 1/4 S squared root 3. And there it goes. All right. Good old work. Good old work. Let's go to number 47, critical thinking. 48 is also critical thinking. Sip of water for critical thinking. The area of a regular pentagon is 72 square centimeters. Find the length of one side. So area is 72 square centimeters. This is area is 1/2 apothem times perimeter. Two variables, but they do have a relationship. As long as we have the central angle measure of this pentagon, we can relate one in terms of the other, I'm sure. That'll be fine. Remember, the perimeter is a portion of, it's a combination of all your side lengths. So I'll probably dive into perimeter later with all this. Let's kind of start with, well, I don't know what to start with here, but the 70, pentagon. Pentagon is 72 square, pentagon is 5 sides, 360 divided by 5 is 72, divided by 2 is 36. We've done a lot of those. So 36 here, here's A. X is something I need to find. Now, perimeter is 5 sides times a 2x length of a side, so 10x. When I find X, I can associate perimeter like that. I still don't have any side lengths. So what do I do here? Apothem and perimeter have a relationship as well in that I can use, well, I can do this. Tangent, they have this. Tangent of 36 is x, not perimeter, but is x over A. So A can be rewritten as x over tangent of 36 degrees. So okay, so here's what I'm going to do. I'm going to reassociate A in two different ways. I have A also up here. If I multiply both sides by 2, I get 144 is apothem times perimeter, and divide by perimeter, I get apothem is 144 over P. Basically, I'm getting A associated in two different ways here. Oh, hold on. Perimeter is 10x, so x, I don't want multiple variables here. X is perimeter over 10. Ugh, this is going to get ugly. So apothem is perimeter over 10 times tangent of 36. That's a lot of kind of work to get done there. So I have two different ways that I'm associating apothem. 144 over the perimeter and perimeter over 10 times tangent of 36. That kind of makes a system of equations where I can then set those two things equal to each other to find perimeter. I don't think I lost myself in my work, but I'm sure I lost you guys a little bit. This is a critical thinking problem. If you're in the problem, got to keep up with the critical thinking. The problem is there's multiple variables, and I'm using x. X isn't a real variable thing I use, right? X is more so an association with perimeter. So rewriting x in terms of perimeter allows me to use that here, and I have two different ways I've associated apothem. So what I want to do is set these equal to each other. I got 144 over P equals P over 10 times tangent of 36 degrees. So I'm going to solve for P, and then use that to find the length of a side. We'll divide that by 5. So cross multiply, we get P squared equals, that's 1440 times tangent of 36. And take the square root of both sides, I get P is square root of that. I'll just leave that kind of like that. And here's the thing, I don't want to round that early either. A side length, S, I'm trying to make an S and not make it look like a 5. S is going to be 1/5 of that, right? S is 1/5, see the difference? 1/5 of 1440 times tangent of 36, because perimeter is 5 times any one side. So let's do that. Let's go to our calculator. I'll just type it. 0.2 is 1/5 times square root of 1440 times tangent of 36, and I'm getting 6.469. What do I want us to round? I'll say 6.5. Around 6.5 centimeters. So that's the length of any one side in that. Now, I could double check by going back and doing this whole thing over, and they say a side length of a regular pentagon 6.5, and find the stuff, find the area. How are we able to get that one so much easier than what I just did here? There must have been another way I could have come up with. I don't know. I guess that's the only way I really thought of in my head to make that thing work. But I'm going with the 6.5. I think it feels legit with what we're doing there. What problem is that? 47. Okay, so let's keep moving on. Let's go to number 48. Okay, number 40. Oh, it's right here. Duh. Number 48, critical thinking. The area of a dodecagon, 12 sides, is 140 square inches. Find the apothem of this polygon. Well, this is the same kind of problem as what we just did. So 140, I feel like there's a faster way to do that though. I mean, geez, 1/2 apothem times perimeter. So 12 sides. Perimeter is 12 of those S's, right? But the S, oh geez. I'll just do what I did last time. Let's just do what we did last time. So let's get the apothem portion by itself. This time let's try and get the perimeter portion by itself. Then I can, in terms of apothem, then I can set those equal to each other and just find the apothem then and there. So I'll do something slightly different here. So perimeter is the 12 sides multiplied, but any one side is these S's here, whereas the X that I use is this guy. Now when it comes to the apothem, there's still the ratio relationship of that. There's a trig relationship that they have together. So we got to find the central angle. So 360 over 12 is the central angle measure of 30. Therefore, this is 15 degrees. So the tangent of 15 degrees is X over the apothem. This time, let's get X by itself because I'm going to associate and get apothem in its own way. So X is the apothem times tangent of 15 degrees. Now, I started setting up this other one over here. Perimeter is 12S. Let's keep going. Let's keep navigating that. Perimeter is 12S, and X is, S is 2 X's. So perimeter is 24 X's. And X is A times tangent of 15 degrees. So perimeter is 24 times A times tangent of 15 degrees. So there's something in terms of A that we can use. I feel like that's kind of in the wrong spot though. Let's put that at the end. Let's do 24 tangent of 15 degrees times A. Otherwise I kind of lose it. Times A. I think, right? Is that where we normally put a variable? I don't know. I normally don't do it with a trig like that. Maybe we put it in front. That's okay. We'll leave it there. Anyway, we also have this ratio relationship, or this relationship up here, getting perimeter by itself. Multiply both sides by 2. You get 280 is apothem times perimeter. And divide both sides by A. You get perimeter is 280 over A. So now I have one where I can get A by itself. I got perimeter equation there. P equals this and P equals this. Let's set those two things equal to each other, where we get 280 over A equals 24 times tangent of 15 degrees times A. I will multiply both sides by A and divide both sides by 24 tangent of 15, and I get A squared equals 280 over 24 times tangent of 15. This can reduce a little bit, and I suppose I will. 28, oh wait, hold on a second. Hold on, let me see what that is. 280 divided by 24. Oh, it's 11.6 repeating, so it's not a perfect one. What's that fraction? It's 35 thirds. So A squared is 35 over 3. I guess that doesn't matter. I'm still going to be taking the square root. I wanted to try and get kind of a decimal answer. So A is the square root of 35 over 3 times tangent of 15 degrees. Yeah, quite a bit of work there, and I only hope that it's probably reasonable with what I want to do. So square root of 35 over, and I need parentheses on the bottom, 3 times tangent of 15. I'm getting around 6.598. It's around 6.6. What's this? Inches? A is around 6.6 inches. That's my apothem. So the only difference that I did with that problem compared to the previous one was I went ahead and associated A, like getting that one by itself, if that makes sense. Where, not A, sorry, excuse me, I got P by itself to express in terms of A, so I didn't then solve for a P and then plug it into one to solve for A and like, don't round early and oh, you got to type all that stuff. I think that'd be quite a bit. That definitely is critical thinking within. I feel like there's probably faster ways to do it if the other way is so much quicker that if I just have an apothem for the stuff, I can find them much faster. And I just don't know. I didn't come up with it if there is one, but I still got them. in my head, I still got what I think the answers are. All right, we have 4 more questions. No proofs, but using structure. Okay, using structure, thought-provoking, comparing methods, and using structure again. In the figure, an equilateral triangle lies inside a square, inside a regular pentagon, inside a regular hexagon. Find the approximate area of the entire shaded region to the nearest whole number. I won't round early. What we do see is all of them have a side length of 8. So, how much work will we have to do here? I think with the triangle and the square, and maybe even the hexagon, we have a formula for regular hexagon. The pentagon's the only one that's going to need more work. So, check this out. The triangle, let's do that bigger. We got an area for that. It's good to recall previous information. They didn't say you couldn't use any means necessary. I'm going to use any means necessary. So, the triangle, I'm not even going to do the 1/2 apothem times perimeter. I'm going to do this. 30, 60, 90. It's an equilateral. Half of 8 is 4. So this is 4 root 3. So the area of the triangle is 1/2 base of 8, right? That's still the whole base, times height of 4 root 3. And that's going to be 16 root 3. Square units. It doesn't really say what it is. 16 root 3 square units. No rounding. Square. The area of the square is 8 squared, which is 64. Now, we need the area of the shaded region. Before I do the pentagon and hexagon, before I do the pentagon and hexagon, the area of those two is going to be area of small shaded is going to be 64 minus the area of the square minus the area of the triangle. So 16 root 3. So we have that guy. That's going to add with the area of the bigger one later. So we got some stuff. Let's do the area of the hexagon next. What I did on this problem here, this was the area of a regular hexagon with a side length, half a side length that was x. Half the side length is x, half is 4. So 6x squared root 3. 6x squared root 3. Let's trust that we got that right, that I got that answer right. Area of the hexagon is 6 times x squared root 3. That's 6 times 16, which is 96. So 96 root 3 square units. I'm going to trust that what I got for my formula I can use. Perfect. As far as the pentagon goes, we have a little more trig work to do. So for the pentagon, we got, let's do that again. We got half of this is 4. We've seen 36 degrees quite often with this pentagon. We need to find this A. We know the perimeter will be 8 times 5, which is 40. And the apothem here is going to be, tangent of 36 is 4 over A. So A, So A is, tangent of 36 is 4. A is 4 over the tangent of 36. So we've done a few of those as well where they kind of switch places. So the area of the pentagon is 1/2 apothem times perimeter. That'll be 80 over tangent of 36. So the area of the bigger shaded region, of the BS, abs, is the area of the hexagon, 96 root 3, minus the area of the pentagon, 80 over tangent of 36. So the area of the total, the area of the whole shaded region, will take 96 root 3 minus 80 over tangent of 36, that portion, plus the other portion. I don't really need parentheses around, but I just want to show it. 64 minus 16 root 3. So again, I don't really need parentheses. I'm just going to do those in the calculator. So let's go to the calculator. And let's do 96 root 3 minus 80 over tangent. Now, the reason we subtract these two is because that just gets the shaded region of the hexagon minus the pentagon. It just gets what's around that. tangent of 36 plus 64 minus 16 root 3. And yes, I could have combined the 96 root 3 and 16 root 3 and whatever. But they said round to the nearest whole number anyway. So this is 144.44. So to the nearest whole number, that would be about 144. So I don't know. I don't know if that's right. 144 square units. Let me kind of like work over all the hexagon stuff, make sure everything looks good, and make sure that I kind of added things correctly. Hold on. Okay, I'm back. And before I had to go do some stuff. Before I continue, I didn't do 80 divided by tangent of 36. So this should be, so that's going to change the answer, right? So that, boom. And, all right, so 92.45. So I forgot what I had before, 144.44. I'm going to write 90, nearest whole number, around 92 square units, I believe. So that was one thing I caught before I move forward. Sometimes that happens when I try and click on the things fast. I don't think it always registers my hits, so I got to be careful on that. Okay, we got a few more questions left. Let's take a look at number 50. Thought-provoking. The area of a regular n-gon is given by a equals 1/2 AP. Yes, as n approaches infinity, what does the n-gon approach? Well, a circle. What does p approach? The circumference of the circle. What does a approach? The radius of the circle. What can you conclude from your three answers? Explain your reasoning. Okay, well, I kind of just said them all out loud. So as I kind of answered this in a previous one when they talked about if you have a fixed radius for this thing, what happens to the areas? It keeps going up. So as n approaches infinity of a regular n-gon, the n-gon approaches a circle. The perimeter approaches its circumference, and the apothem starts to get closer and closer to the radius, approaches the radius. My conclusion is that the area of an... Oh, I don't know if we want to calculate something or not. So let's try this. This kind of goes to the area of the circle they already gave us before. Area is 1/2. Now if your apothem is radius times perimeter circumference, you get this. 1/2 of, 1/2 times 2, whoops, 2 pi r. 1/2 times 2 is 1, and r times pi times r is pi r squared. So, conclusion. There we go. All right, I'll deal with that. That looks good. Number 51. So the area, you get the area of a circle, basically. So number 51, area of a circle obtained. All right, number 51, comparing methods. Find the area of a regular pentagon ABCDE by using the formula A equals 1/2 AP or A equals 1/2 area times the number of sides times side length. Then find the area by adding the areas of smaller polygons. Check that both methods yield the same area. Which method you prefer? I prefer the 1/2 AP thing in general. You can use this other stuff. Now, with the ABCDE, they show you an isosceles triangle and an isosceles trapezoid for the areas which we got to find. I'm sick of pentagons, though, in the sense that it's not trig-based. I don't have a formula for it, really, and I've used that 72 over and over. So let's find this using 1/2 AP. Remember, in this case with the center, this is going to be 36 degrees. We have a side length of 5, so half of that is 2.5. I need the apothem here. Tangent of 36 is 2.5 over A, so A is tangent of 36 over 2. Wait, hold on. Did I say that right? A is 2.5 over tangent of 36 degrees. So there's my apothem. Perimeter we have as 5 times 5, so 25. So area is 1/2 apothem times perimeter. Sorry for the sloppy handwriting there. So that's about, let's just round that one. So 0.5, what did I just do? 0.5 times 2.5 times 25 all over a tangent of 36. Just kind of writing it out of order. It should still be the same thing. 43.01. So around 43.0 square units. Okay, so there's an answer. Let's find the answer using this triangle stuff. Triangle and trapezoid. Now, given their isosceles, these are still 5s and such. This triangle, this is a, gosh, how do I say this? This is a regular pentagon, and its interior angle measure, each interior angle measure is 108 degrees. What you're doing is your interior angle sum is 180 times the number of sides minus 2. That becomes 540. So I becomes 540 divided by 5, which is 108. So if that's 108, then one of these is 54 degrees, which goes in right there, which means I can use trig to find out one of these side lengths here, which I'll call x. And if I get that x value, then I can figure out kind of what goes there for the triangle. Okay, we can either do two different congruent triangles or the entire triangle's length there. So the sine of 54 is x over 5, so x is 5 times the sine of 54. So 2x is 10 times the sine of 54. That's the entire base of not only this isosceles triangle here. Oh, and I still have to find the apothem. Not the apothem, the height of this triangle. Cosine of 54 is h over 5, so h is 5 times the cosine of 54 as well. So, yeah, definitely I don't prefer this way. Area, it says explain your reasoning because this way sucks. The area of the triangle is 1/2 base times height. Sorry. Which is 25 times the sine of 54 times the cosine of 54. Okay, so there's the triangle. The trapezoid is going to take a little bit more work. Now, because I have to find, oh, no I don't, that's just 5. That's easy. Okay, so that's 5. I do still have to find this height though. I have to find this height here. I'll call it y. In order to find that y, I have a 5 here and 90 and 108. Okay, this is going to take a little bit of just pointing at. So this is 90 degrees here. The whole interior angle is 108. That makes this 18 degrees. So cosine of 18 is y over 5. So y is 5 times the cosine of 18. You know, I don't know how many people I speak to at this part of this problem. If you're asking these kinds of questions or you're assigned them, then it's assumed that you know what I'm working on with this. And so getting that why, this isn't I'm just learning this for the first time. Help me answer question number 51 on this thing. No. If you're watching this part, then you're kind of discovering this stuff with me. So it's going on. Because the area of a trapezoid is you average your bases and multiply by your height. So it's 1/2 of this base here of 5 plus this base here, that 2x, it's 10 times the sine of 54, and multiply that by your height. And height is 5 times the cosine of 18. So I don't really know what to do in terms of rounding, so I'm just going to go ahead and write it like that right now. So 0.5 times 5 plus 10 times sine of 54 times 5 times the cosine of 18. Now this is some number. This is 31.1 something. 31.1 something. And we have to add that with the area of the triangle. The triangle's area was 25 times sine of 54 times cosine of 54. Now that rounded, 25 sine of 54 times cosine of 54 is 11.88 something. 11.8, 11.9-ish, 11.9. So together, when you add those two, area of triangle plus area of trapezoid, and I'm going to use my exact answers that I have in my calculator here. Let me show you my calculator. When I do these ones, I'm going to take this plus, oh, how do I do this best? I'm going to do the previous answer I did here plus the previous answer there. Together I get, oh, I must have done something wrong there. Because that should have just been 31 plus 11. Okay, let me go back then and do that again. I want to do this plus 25 times sine of 54 cosine of 54. And that's, no, something's going wrong. Why did first time I got 31.1? Hold on a second. Something's going wrong here. Something here. Oh, I'm still inside. I see. I'm still inside my cosine. I need to close that parenthesis. Okay, let's do that again. All right, 43.01. So what is that? Around 43.0. Now, last time I got 43.0 as well. That was a lot less work. A lot less work. I prefer... I'm not going to explain why. The work is going to be just fine. A equals 1/2 AP. I'm sure you would as well. Depends on the problems. But because like a square or a triangle, I might do something else. All right, number 52 using structure. Last question. Two regular polygons have both end sides. One of the polygons is inscribed in and the other is circumscribed about a circle of radius r. Find the area between the two polygons in terms of n and r. So let's draw a circle with a center kind of, yeah. And I'm going to make up a polygon. Let's do like a hexagon. It doesn't matter what the thing is. I just need to do something that looks inscribed and circumscribed and stuff like that so we can make sense of what it is we're talking about. Let me try that again. So one of them circumscribing it and one of them inscribing it. So boom. Like that. And then one on the inside. I mean, I could have drawn anything. Could have done a triangle or whatever else as well. Wrong shape. And then like boom inside like that. Probably use different colors here, right? This can get you a little blind into what's going on. So I have a blue. I have a green. And I have a purple. Okay, so the idea here is the circle has a certain radius. Let's do the green color for that. The circle has a certain radius of r. So that's also the radius of this guy. Now, that's also the apothem of the purple one. So let me actually do this. Instead of the circle actually doesn't matter too much to me. What matters is the blue guy's radius is the same as the circle's radius, and the circle's radius is the same as the purple guy's apothem. Let me do the apothem one up here. I'll do two different triangles, one on top, one on bottom. So the circle I don't think matters anymore. The circle was to give me r, and now I can see where r exists in both of these. Remember, n is just number of sides. It doesn't matter what kind of shape this is. So this is r, and this is r. They're both the same length. So when it comes to the smaller one, what we have to do is work off the central angle to get the apothem. And remember, this is not a hexagon. This is some n-sided shape. So the central angle here is going to be 360 divided by n, and then half of that. So 360 over 2n, or 180 over n degrees. So if I want to find the apothem, I will use my radius and use cosine. I'll say the cosine of my 180 over n degree value is a over r. So a is r times the cosine of 180 over n. Our final answer for this whole thing has to be in terms of n and r, and this is getting it started. Now the perimeter, we just have r, right? We have r, and then we know that n is the number of sides. So the perimeter, let's get this x value. Let's double it to get s, right? The way that I've been doing that before. And then p is going to be, n times that many things. So x is going to be with the same trig stuff. X is 180 sine r times 180 times sine of 180 over n. We've done that stuff before. So 2x is twice that. So the perimeter is twice the x's. hold on a second. I can't really use x in this thing, right? Oh, twice the r. 2x is 2 of the r's. So perimeter is 2 r times n. I don't really know where else to put it. Times sine of 180 over n. That's fine. I don't really know how else to put that. So the area of the smaller one, is 1/2 apothem times perimeter, 2rn sine of 180 over n. Now this can simplify a little bit. The 1/2 times the 2 can cancel. The r times the r can become r squared. So ultimately for a sub s there, we'll have r squared, let's put the n first, n times r squared times the sine of 180 over n times the cosine of 180 over n. So therefore, for every single shape here on out where we have the radius number of sides, I can use this formula. All right. So I think that's a final answer for that one in terms of r and n. The purple one, on the other hand, we have the apothem represents the radius, which is r. The radius is r. So if I want to find the apothem, listen, I have the same central angle. 180 over n is still this guy. It's this guy as well. It's the same kind of thing when it comes to central angle measure. This time I need to get the x based on the apothem being r. So for this guy, the a is r. And the x, I can use tangent. I can solve for x. So tangent of 180 over n equals x over the apothem, which is r. So x is r times the tangent of 180 over n, right? That's the goal. Get this in terms of n and r. So 2x is 2 of these, and the perimeter is going to be 2 times n times r times this, tangent of 180 over n. So I have my apothem and my perimeter. So this one will be the area of the bigger guy. Area B is going to be 1/2 apothem times perimeter. And that can simplify to the 2's cancel and r times r is r squared. So a sub b is n times r squared times tangent of 180 over n. 180 over n. So here's that area. I'm kind of out of room on this space thing except for what you can see. Oh, you probably can't even see what I'm writing. I'm sorry. Just the space is going to go like that. I apologize. So we have this one, and let's copy and paste the other one as well. So on this here, I have this as well. Here are the two. What's the question? Find the area between the two polygons. So we're going to subtract. So area between equals the big minus the small. I can do nr squared. Listen, I can factor nr squared out of both terms, and I'm left with the tangent of 180 over n minus the sine of 180 over n, and these can't factor, times the cosine of 180 over n. That's really nifty. When you subtract one and the other, you get the area in between them. Super, super nifty, and that's what I'm going with. I gotta trust my own work as far as they both look cool, right? They look like something that would kind of work out for me as a whole. I'm just gonna go with it. I don't know, but that's factoring the nr squared out of that. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Next would be the 11 point. I had to pause this thing. It was showing some show, and I don't want to get a copyright thing. Now it's just showing ads. But anyway, we're going to do 11.1 to 11.3 quiz review coming up next after this. And then after that, I think what I always envisioned would be chapter 11 on volumes and solids and stuff like that. I thought it was all on volume and surface area. I don't know if we're doing surface area, but we're for sure doing volume. And then doing this stuff matters. Doing the arc length, the areas of stuff all matter there. So I think it's good that we did all that to begin with. That'll be the latter half of this chapter from 11.4 to 11.7. So thank you guys so much for watching. Take care, and I will see you in the next one.